All right, here we're going to talk about dilutions. And dilutions are important because, like as for instance, if you're doing a lot of work with different concentrations, you maybe don't want a shelf that's full of 10 different bottles of the same things at different concentrations. It might be easier to have just like one really concentrated thing, and then you can dilute it to get whatever concentration you want when you want it. Also, since a more diluted solution just has more water, it takes up a lot more space. And you'd see this, on the shelf in a chemistry lab, but you'll also see this on the shelf in a pharmacy, right? So that you'll have maybe a very concentrated saline solutions that need to be diluted in order to be appropriately used as an IV bag, so that you don't cause tissue damage, kind of a thing. But so they're pretty widely used, and there's an easy formula for dilutions, and I don't give it to you, so you have to memorize it, just like everything in this chapter. You just have to memorize it. But it is the initial concentration times the initial volume is equal to the final concentration times the final volume. Now I know in my lecture notes, I think I give it as M1V1 equals M2V2, where M is like molarity. You can do it with molarity, but you can actually do it with any concentration unit. So you could do it with percentages, you can do it with parts per million. So long as you have the same concentration units on both sides, it totally works. All right. So again, this is saying my initial concentration times my initial volume is equal to my final concentration times my final volume. Now, do you remember every concentration unit we've used, every single one has some amount of solute divided by amount of the whole solution. So what happens here with our dilution equation is that if you multiply by the volume of solution, those cancel. And what's really left is the amount of solute, which when you're diluting by adding water, that stays constant. And that's why these two things are equal to each other. You're saying the amount of solute in the initial solution is the same as the amount of solute in the final solution. And if I increase my volume, then that's gonna decrease my concentration so that they're always equal to one another. Does that make sense? Okay, so let's do this problem from the lecture notes just to kind of try it out. It's not really hard if you remember the equation, and that's, I'm gonna put a big like red box around here to help you. Like, you've got to memorize this guy right here. All right, so they give us, you have a 0.5 liter sample of 0.1 molar sodium hydroxide. I add water to dilute the solution volume to 2.5 liters. What is the final concentration? So just again, like we did with our algebra problems in chapter 8, or the chapter on gases, let's just label these. So this is my initial volume, and this is my initial concentration, right? Molarity is unit of concentration. My final volume is 2.5 liters. And I want to know what the final concentration is. That's C2. I'm going to solve for C2. So if I solve for C2, what is that equation going to look like? Yeah, I'm going to have C1 V1 on this one side, and then if I divide both sides by V2, that's going to be equal to C2. Divide by V2, those should cancel. All right, so now we can just plug it in. And again, I just like to solve it before I plug numbers in. It keeps things really cleaner. All right, so that gives me C1, 0.10 molar NaOH, and V1, 0.500 liters solution divided by V2, which is, 2.500 liters of solution. All right. So in that case, and you see, if we leave our units, the liters cancel, and we're going to be left with units of molarity, which is great because I'm solving for concentration. So it better be something like that. 2.10 times 0.5 divided by 2.5. I stuck it on exponent and now it's never going to let me leave it alone. All right, that gives me 0.02 molar solution of NaOH. Erica reminds us that we do dilutions with rubbing alcohol too, right? You might be able to buy rubbing alcohol as like 70% at the store, but you might only need 30%. So you can dilute it to get what you want from that. Excellent. Any questions on this one? Do you want to do another one? Do you feel good about that? Well, Zach's got a great question. He says, if one of these units was in milliliters and one was in liters, you'd have to convert it. The answer is yes. If liters and milliliters are units of volume, right? So if V1 was in milliliters and V2 was in liters, it wouldn't matter which one you used, right? You could convert V2 to milliliters, so they both canceled. Or you could convert V1 to liters, so they both canceled. But you have to have the same units in this formula for them to cancel, as you can see. This worked because they were both liters. Does that make sense? Okay. All right. Next, let's do, well, we usually do a couple of, let's do just one of these here from your worksheet. It's pretty straightforward, but you will want to make sure to pay attention to the wording here. All right, so how much water would you add to, we have 100 milliliters, 0.5 molar sodium hydroxide, if you want the final concentration to be 0.150 molar, okay? So this is my initial volume. This is my initial concentration. My target concentration is right there. So we're going to solve for V2. So if I want to solve this equation for V2, I'm going to divide both sides by C2, right? And I'm going to get C1 V1 over C2 is equal to V2. I'm looking for, I don't know what I gave you, 3. Okay. Does that make sense? Everybody believe me? Okay. All right, so the C1, 0.500 molar, NaOH, multiplied by the V1, 100 milliliters. I'm going to make a little mental note that I'm in milliliters here. C2, 0.150 molar NaOH, same thing, okay. So when I solve this, because my molarity cancels, my answer will be in milliliters because that's the units that was there, right? Good. Zach has the answer to this. My final volume will be 333 milliliters. Now, this is where everybody loses points because this is the correct final volume right here, but it is not in fact the final answer because they did not ask what the final volume would be. This is where I say, watch the wording of the question very carefully. What do they actually want to know? They want to know how much was added. That's right. So if this is my final volume, and I initially had 100 milliliters, and that's my initial volume, how much do you have to add to 100 to get to 333? Sarah has it right. You just subtract one from the other, and you'll see 333 minus 100 is going to give me 233 milliliters of water. That's what you have to add to the 100 milliliters so that your final concentration will be your final volume will be 333 milliliters, which gives you a final concentration of 0.150 molar. Does that make sense? Okay. Now, Sarah asked an excellent question. She says, do you have any useful tips on how to remember when, like, we need a specific unit, like I have to be in grams and milliliters, or I have to be in moles and liters, versus when do they just need to be like the same on both sides? And the answer is, especially for gases, temperature just always has to be in Kelvin, just always Kelvin, no matter what I'm doing. But other than that, the important thing to note is if you are comparing initial to final, then units just have to be the same. So for the individual gas laws, for the combined gas laws, for this is a comparing thing, right? Dilutions, comparing initial conditions to final conditions, then whatever my concentration units are, so long as they're the same, I'm good, right? And whatever my volume units are, so long as they're the same, I'm totally good. But if I'm not comparing, if I'm using a formula that is not comparing, right? Which, like the ideal gas law, it doesn't compare initial to final conditions, right? It's just like, these are the conditions. Or if I'm saying, hey, calculate molarity, that's not comparing initial to final. It's just like, okay, this is the units for molarity. Then you have to use the units defined for that system, essentially. Does that make sense? So this is the key here. If I have like a 1 and a 2 in there, like a V1 and a V2, then it can be whatever you want. But if there's just a V, then you have to say, okay, well, if I'm doing molarity, so that volume needs to be liters. Or I'm doing percentage concentration, so that needs to be milliliters. Or I'm doing the ideal gas law with the gas, that V has to be liters. That's a really good question. I hope that's a helpful answer. I hope that's helpful. Okay. Well, we are now on to our third chapter 9 lecture on even more solution concentration units. Yay! Even more to memorize. Okay, so we've done molarity, which is moles per liter, and we're going to continue using that for the rest of the semester, so make sure you get that down. And we've done percentage concentration, which you see at the drugstore all the time. And we've done parts per million and parts per billion, which is what you see in cases where you have very low concentration units. So like water quality is a place where you'd see parts per million, parts per billion. You might also see it for air quality, right? You might see that kind of solution concentration units. Next, we're going to do units of equivalence. And equivalents are actually pretty narrowly used, I think, in the healthcare field, although they might be used in other places I'm not as aware of. But an equivalent is used when you're looking at a solution that has lots of different ions and you're kind of only interested in one of the ions. So like as for instance, if you're doing a blood draw and we're looking for the amount of iron in your blood. Well, okay, yes, we can look for iron in your blood, but like there's lots of other things in your blood, right? There's sodium, there's potassium, there's chlorine, there's bicarb, there's phosphate, there's a whole bunch. There's a bunch of stuff in there, right? It's a mixture. And because it's in solution, all of these ionic compounds have separated. So it's not like I can say, I'm looking for the concentration specifically of iron chloride, or I'm looking the concentration specifically of iron carbonate or iron phosphate. They're not associated with one another. They're just floating around separately. So it would be silly for me to ask for the concentration of like a molecule in that case, because they're just disassociated ions. Does that make sense? Okay, these are used when we are interested in the concentration of only one ion and a mixture of ions in solution. Okay, so you'll see this kind of unit given if you go in and get a blood test and your doctor's reporting how much potassium is in your blood or how much magnesium is in your blood or how much iron is in your blood. He might give you these answers, or by he, I mean the lab who does the testing, might give those answers in equivalents or milli-equivalents. All right, so what an equivalent is, one equivalent is equal to 1 mole of single charges. And it could be plus or minus, right? So one equivalent of negative charges is 1 mole of -1 ions, right? One equivalent of single charges could be 1 mole of +1 ions. But if your ion has a charge that is higher than +1 or -1, then you would say, look, for instance, magnesium has a charge of +2. Hang on a second, I'm getting ahead of myself. So like one equivalent of chloride ions, because chlorine has just a charge of -1, that's the same thing as 1 mole of chloride ions. And one equivalent of sodium ions, because it's just +1, equals the same as 1 mole of sodium ions. But if I wanted to do one equivalent of magnesium ions, which have a charge of +2, well, 1 mole of +1 ions is only going to take half as many moles of magnesium. So 1/2 a mole of Mg2+ ions is going to be one equivalent, because you take 1/2 a mole times a charge of +2, that gives you 1 mole. It's like the same as 1 mole of +1s. Does that make sense? You're going to divide, essentially you're going to divide by the charge. So one equivalent of iron, if you're looking at that, of 3+, is going to be, because you have +3 charge in a single mole, then it's going to take 1/3 of a mole to get equal to like one equivalent +1 charge. So yeah, exactly. You just divide by the charge is exactly what you do there. And it works for polyatomics as well. Whoops, so you could say one equivalent of SO4 with a 2- charge. Whoops, SO, that's supposed to be 4. There's your sulfate. Is going to be just 1/2 a mole of sulfate ions. Yeah, perfect. You got it, Nicole. Because you take that -2 multiplied by half, that gives you one equivalent ion. And again, yeah, it doesn't matter if it's positive or negative. So we can have an equivalent of positive ions and an equivalent of negative ions. And what you find is that in solution, of course, if you've got a mixture of ions, they still have to balance. So you have to have the number of positive equivalents has got to be equal to the number of negative equivalents. I'm never gonna like test you on that, but that's essentially what it comes down to. So if you've got a big mixture and you've got a whole bunch of cations, a whole bunch of anions, you should be able to add up the number of equivalents and they'll be equal. But this is what it is. So just to give us an idea. And anyway, so this can become a conversion factor here, right? One equivalent is say like 1/2 of a mole. Or if you were looking at it in terms of grams, right? You would say, well, if 1 mole of magnesium is, gosh, I don't know, 24, look it up on the periodic table, 24.31. Okay, I was off by 0.31. 24.31 grams in 1 mole. So 24.31 grams divided by 2 gives me 12.15 grams of magnesium 2+. And so that's the number of grams in one equivalent, right? If it's 1/2 of a mole, it's 1/2 of that molar mass. That's the number of, I can see this is the number of grams in the equivalent. This is the number of moles in one equivalent. This is a conversion factor. Now I'm going to do dimensional analysis. So, like as for instance, if the doctor were to calculate the amount of iron in a blood sample to be 0.00120 grams, we can calculate the number of equivalents that is, right? We want to go from grams to equivalents. All right. Well, we know that one equivalent is 1/3 of a mole. And if I look up on my periodic, handy dandy periodic table here, iron is 55.85 grams in a mole. This is equal to 55.85 grams, which divide that by 3 because we're in 1/3 of a mole. So the number of equivalents here, let's see, there's one equivalent. Oh, you're not helpful. 55.85 divided by 3. We have 18.62 grams of iron, 3+, in one equivalent of iron, 3+. Zach, I'm not sure of your question, but to get from your equivalents to moles or equivalents to grams, you divide by the charge, right? So if your charge is +1 or -1, then you just divide by 1. So one equivalent is the same as 1 mole is the same as the molar mass, depending on whether you want to convert between equivalents and moles or go straight from equivalents to grams. But if you have a charge of +2 or +3, basically anything other than +1, you have to divide the number of moles by that charge number. So if your magnesium +2, one equivalent is 1/2 of a mole, and it's going to be 1/2 of that molar mass if you're looking to go straight to grams. Does that answer your question? Good. Okay, so if we have 0.00120 grams of Fe, we're going to say 3+. Here they say iron. They didn't tell me what ion. That's critical error, except actually just above this section it does refer to iron 3+. Okay, and then you say, I know that every one equivalent has this many grams in it. So one equivalent, Fe 3+, has 18.62 grams, Fe 3+. There we go. Yeah. 0.00120 divided by 18.62. That gives me 6.44 times 10 to the -5th equivalents. Now, one thing that you see is that sometimes these solution concentration units can be kind of small. And so more often they don't actually report your answers in equivalents. They're going to report your answer in milli-equivalents. Ooh. All right, so let's say I wanted to take it further and convert that to milli-equivalents. How do I do that? Yeah, Sarah's right. And this is why we love the metric system. Because if I want to convert from equivalents to milli-equivalents, I just learned about equivalents literally 2 seconds ago, but I know what that conversion factor is. There's 1,000 milli anything in one of that thing. Right, 1,000 milliliters in a liter, 1,000 millimeters in a meter, 1,000 milli-equivalents in equivalent. Why not? All right. Multiply that by 1,000, and we get 0.0644 milliequivalents. Like that. Does that make sense so far? All right, now of course, we aren't doing concentration yet. We're just referring to amount. And so to make this concentration, we need amount of solute. Hey, we just did that. Divided by amount of solution. So to express equivalence in concentration, you're going to divide by the volume of solution tested. So like as for instance, I say, hey, by the way, this iron sample was in 50 milliliters of blood. And I want to know what is the concentration in milliequivalents per liter. But sorry, I'm running out of space here. Is okay. In that case, you're going to say, all right, now I know the milliequivalents. I've done that bit. And I just need to get liters on the bottom, and they gave me milliliters. So this is just, again, it's just dimensional analysis. And we can we could just start from where we were, 0.0644 milliequivalents, Fe3 plus. And then we are going to say, I want my amount of solution on the bottom, which was 50 milliliters of blood solution. Okay. But they wanted liters on the bottom. They specifically said milliequivalents per liter. So I'm going to have to do that thing where I remember that there's like 1,000 milliliters in 1 liter. Of anything, including blood. So we're going to cancel that. And that gives me milliequivalents per liter. And all right, there's my 0.0644 divided by 50 times 1,000. And I get 1.29 milliequivalents per liter. Does that make sense? All right. Sarah says, I'm getting it, but I don't like it. I like the honesty. I appreciate that. Let's do a couple of these problems from the worksheet that might help us feel a little bit better about it. Okay. So here we go. We've got a solution with sulfate at 0.025 molarity, and we want to convert that to milliequivalents per liter. So to do this, first thing we have to do is say 0.025. What does that capital M mean? It's so useless. Good. Moles of sulfate, SO4 2 minus, you gotta remember that, in every 1 liter of solution. That is exactly what molarity is. Now they want me to convert that to milliequivalents per liter, which is not so bad because look, I've already got liters. Gave you half the problem. Now all you have to do is convert from moles to milliequivalents. So how am I going to do that? Sarah's exactly right. I've already got moles here, so I'm going to note that 1 equivalent for sulfate, because it's got a 2 minus charge, it's the same thing as half of a mole, or 0.5 moles of sulfate. If it makes you feel better, you could also just say 1 mole of sulfate is 2 equivalents. Does that make you feel better? To be like, because there's a 2 plus charge, then every 1 mole is going to be 2 equivalents. That means the same thing. Do you guys like that better? Sometimes students just don't like fractions. Yeah, so because it's got a 2 minus charge, so 1 mole of sulfate is like 2 moles. sulfate with a 2 minus charge is like 2 equivalents of something with like a 1 minus charge. We can totally do that. Some of you guys might be like, no, don't change it now. It was hard enough to begin with. I apologize. I'm going to change it now because 1 divided by 1/2 is the same as 2 divided by 1. I should say not 1, 2. Okay. So 1 mole of sulfate, because it's got a 2 negative charge, 1 mole of sulfate is the same as 2 equivalents. This is the same thing as saying that 1 equivalent is 1/2 of a mole. 2 equivalents is 1 mole. Okay, and then Nicole noted that I've got a molar mass here, but guess what? I don't need that molar mass because currently, just by doing this, that gets me to moles, or sorry, that cancels my moles, I get to equivalents, and what they really want is milliequivalents. So to go from equivalents to milliequivalents, I'm just gonna do, yeah, because I'm already at equivalents. So here we compared equivalents to moles, and we also compared it to mass, and it just kind of depends on whether we're given mass to begin with or moles to begin with. Yeah. 1,000 milliequivalents in 1 equivalent. Good. So my equivalents cancel, and I've got milliequivalents per liter, which is exactly the units that they asked for. So 0.025, multiply that by 2, multiply that by 1,000, and the solution here is 50 milliequivalents per liter. Right there. So this is just a little bit more dimensional analysis. All right, if we do this one, normal blood contains 3 milliequivalents per liter of magnesium 2+. So they want to know how many milligrams do I have in 100 milliliters of blood. And I'm just going to fall back a little bit on our old strategy of just, okay, step 1, identify the units. I want milligrams of magnesium 2+. Okay. And step 2, what did they give us? They gave us, we have 100 milliliters blood, and we have 3 milliequivalents of magnesium 2+ in every 1 liter of blood. Okay. All right, and then what they didn't tell us is what equivalents are, but we know what equivalents are, right? We know that, oh good, yes, Sarah, we're also gonna need, there's 1,000 milliliters in 1 liter. And for magnesium, because it's got a 2+ charge, every 1 mole of magnesium 2+ is equal to 2 equivalents. Do you guys like that better? Sorry if that just confused you. If I totally, Erica says, no, I don't like that better. Don't confuse me. We had it. Okay, we'll keep it. 1 equivalent magnesium 2+ is equal to 1/2 a mole magnesium 2+. Okay. Yeah, they both work. Okay, so to solve this problem then, to set it up, that is a great question. Yeah, how are we going to get from moles to magnesium? We're going to need the molar mass, you're right. And that was 24.31. Okay, I remembered it this time. You guys don't have to remember that. That's why there's a periodic table. Only crazy people like me remember that because I use it all the time in class. Okay, so, this looks like it's gonna be a big dimensional analysis extravaganza. All right, where shall we start? Where even? All right, Sarah wants to start with Oh, hang on a second. No. You're right. Sarah also mentioned I'm going to need that there's 1,000 milligrams in 1 gram. Worse than I thought. Okay. Sarah wants to start with 3 milliequivalents per liter. She always likes to start from beginning. All right, what am I going to do next? Milliliters to liters. Okay, so 1 liter, that's going to go on the top, so those will cancel. It's the same thing as 1,000 milliliters. Good, my liters cancel. All right, next, what shall I do? Oh, I didn't write this over here, but yeah, I'm gonna need this. There's 1 equivalent has 1,000 milliequivalents. All right, so this is gonna cancel my milliequivalents. So far I did use this little guy here. I did use this little guy here. And I didn't anticipate that I was gonna need that, but I did need it, didn't I? Milliequivalents. Okay, I used this guy. All right, what's next? 1 equivalent is 1/2 of a mole. Okay. Or 0.5 in 1 equivalent for magnesium at least. Not true for everything else, but excellent. That takes us, oh, come here, you. Okay. From equivalents to moles. So now I have moles per milliliter. Okay. Now what? I'm going to need more space. One mole equals 24.31 grams. Zach, yes, that's exactly right. We could either say that 1 equivalent of magnesium is 1/2 a mole, or I could say that 1 mole is 2 equivalents. They're saying the exact same thing. Okay, but we've got 24.31 grams magnesium 2+ in every 1 mole. Magnesium 2+. There we go. That used my grams per mole right here. And they asked for milligrams, so that's why the next thing Sarah wants me to do is 1,000 milligrams in 1 gram. So my grams cancel. So now I've got milligrams per milliliter. And now, yeah, very last piece, 100 milliliters blood. Okay. And milliliters cancels. And I'm left with milligrams, which is what I want. And I used this piece right here. And I used this piece at the end. I did use this piece right here. Yeah, I did use that piece. Not that we have to. Sometimes we come up with conversion factors we don't end up needing, but just like trying to track where I've been. This is ridiculous. By the way, I'd never give you a problem on the exam which contained, what was this, 1, 2, 3, 4, 5, 6 conversion factors stacked up like this. That's a little excessive even for me. But I have no problem giving you problems like this to practice. I figure if you get good at something like this, if you practice it, then you can do the 4-step conversion that I might give you on the test. All right, 3.64 milligrams. Is that what you guys got? All right. All right, that is equivalence. Okay. The next thing we've got to talk about here is osmolarity, our last solution concentration unit that you guys have to know. So osmolarity is like molarity in that it is moles per liter of solution, but it's not moles of solute specifically. It's going to be moles of solute particles. And that's going to be a slightly different thing when your solute dissociates into different particles, right? What kind of solutes will dissociate? That's exactly right. This is a property of ionic compounds. If it dissociates, then essentially 1 mole of solute is not the same as like 1 mole of particles, right? Because it's going to dissociate into multiple particles. So if I want to know how many particles there are in a liter of solution, I can't just use molarity, I have to use osmolarity. And I'll be honest, the first time I ever saw units of osmolarity was on an IV bag. Okay, so yes, this is pertinent to what you guys are doing. And it has to do with the fact that, of course, when you're giving somebody an IV drip, you have to have the same concentration of solute particles going in as you expect the concentration of solute particles in the blood to be, right? Otherwise, if you are over or under that, if you are hypertonic or hypotonic, then you're going to cause problems. So we actually have to be careful to pay attention to the osmolarity there, okay? So let's look at, for example, if I have 1 mole of NaCl, then how many moles of particles am I going to have when those dissociate? Like, it's going to dissociate into how many different things? 2 moles particles, because you're going to have basically a mole of sodium particles and a mole of chloride particles in every 1 mole of NaCl. Does that make sense? What if I had 1 mole of MgCl2? How many moles of particles will that? 3. Oh, you got on it. 3 moles particles. Perfect. What if I had a mole of NH4NO3? Trick question. I tricked you, Nicole. Well, you have to look at it. Okay, this is an ionic compound that's made with the polyatomic ion ammonium and the polyatomic ion nitrate. And there's just 1 of each, yes. So it's really just going to be 2 moles of particles, even though you see a lot of different atoms there, because the covalent bonds don't split up, right? If I said I've got 1 mole of CH4, that's going to be how many moles of particles? It's a rude trick. Well, you're right. Okay. So 1 mole of CH4 is just going to be 1 mole of particles, because the CH bonds are covalent. That's not going to split up, right? So look at a covalent compound. Osmolarity is the same as the molarity. But if I am ionic, then I have to pay attention to the fact that I've got different ions. So I expect you guys to still have memorized the ammonium ion and the nitrate ion. And I expect you guys to be able to recognize a covalent compound versus an ionic compound, so that you could say, okay, this is covalent, so they're going to be the same. This is ionic, so it's going to split. And this is a polyatomic ionic, and this is where it will split. And I see that I still only have 2 ions. You guys with me? Sarah's like, I'm with you, but I don't like it. I still don't like it. I hear ya. Okay, but we could do this. It's actually not too bad, because this is the hardest that it gets. The rest of it is just calculating molarity, right? So to find molarity, you just calculate osmolarity and then you multiply by the number of moles of particles. So basically, you're going to take the molarity and then multiply by number of particles that you expect to see in every mole. Just like that. All right, so why do we care about this? Why does this matter? Okay, now you guys probably are familiar with the terms hypertonic and hypotonic. Okay, so hypertonic equals a higher osmotic pressure, and hypotonic equals a lower osmotic pressure, specifically like as compared to another solution. And the other solution that we typically are referring to in this case is blood, right? Higher osmotic pressure than blood, or lower osmotic pressure than blood. And you might be like, what is osmotic pressure anyways? Okay, where does that come from? Well, higher osmotic pressure is just another fancy way of saying higher osmolarity, right? It's a higher concentration of particles, and that higher concentration leads to a higher osmotic pressure, and I don't need that to be black. Okay, so what happens, and this is really, I know it seems weird, but osmotic pressure is essentially what happens. Okay, if you take two solutions and you separate them with a semi-permeable membrane that lets water through it, right, but nothing else. Oh, and you're exactly right. Sorry, I'm going to add this to Sarah's. Isotonic equals equal osmotic pressure. Okay, so if I take, oh, and I need a different color. I need blue for water. Go away. Now it goes away. Rude. Okay. And say I've got water on both sides. I've got this semi-permeable membrane here. And the semi-permeable means that water can go through it, but particles cannot. Thank you. Okay. And if I have more solute particles on this side and fewer solute particles on this side, there is like pressure actually exerted for the water to move this direction. And over time, if you wait for that to happen, what you will see is that your amount of water on the right-hand side goes way down. You still have these little particles. And the amount of water on the left-hand side will go way up to absorb until the goal is to get approximately the same concentration on both sides. It exerts a pressure, moves the water until you have approximately the same concentration. That is the ratio of solute particles per volume of solution, right? So this is osmotic pressure. It's going to exert this pressure, move the water over, and you're going to be like, this is bizarre. Water can travel across this, but you have a higher level of water and a lower level of water, and it's not like flowing downhill like you would think, right? There's like this gravity pressure that would push it this direction, but the osmotic pressure pushes it this direction, and you get this separation. Okay, so this is what you would observe on the bench, and essentially what happens is you are delivering an IV to a person, right? If you're looking inside their veins, you can see, okay, Nicole, you're exactly right. Water will move to make the concentration of particles the same. That's exactly right. Okay. So here you've got blood cells in your blood, right? And they have a certain concentration of solute inside of the blood cells, because of course we're all water-based, whether you're talking about the liquid that the blood cells are flowing through, or whether you're talking about the cytoplasm inside the blood cells, there's a certain concentration. And because water can actually move through that semi-permeable membrane of your cell membrane there, water can go back and forth. I should make that blue to indicate that it's water. Then the concentration of solute particles in the solution surrounding your blood cells and the concentration of solute particles inside your blood cells is the same, because water can go back and forth. It exerts this pressure and your concentration is going to be the same. Now, let's say you put on an IV drip here, and that IV drip was pure water. Well, now you're adding water to your solution here that has no solutes at all, right? So you're making the surrounding area more dilute, and then more dilute than the blood cells. So the blood cells are going to absorb that water, and they're going to swell up until they explode, and that patient died. That makes sense? Okay, now let's say instead of sticking pure water, you're like, no, I know I can't put pure water on that. I need to put salt water in there. So you put very high concentration of salt in here, and the salt comes in, and now this is actually more concentrated than the solutes in the blood. And so water leaves the blood cells so that it can make the surrounding area lower concentration to match. Then the blood cell shrivels, and that patient died. So the solution is you have to give the person, if you're going to give them an IV drip, it has to be isotonic, at least isotonic to what we expect that blood concentration should be, right? If the person is dehydrated, you're not just going to give them pure water. You're still going to give them that isotonic, what you think that it should be in a typical healthy patient. And that should help kind of reestablish a healthy equilibrium of solute concentration inside and outside of the cell. Does that make sense? Okay, so this is the why we care. But bringing it back to here, the interesting thing is when it comes to osmotic pressure and other colligative properties that we're going to talk about shortly, is that they really do look at individual particles. So NaCl doesn't run around as NaCl. It runs around as Na plus and Cl minus. So a mole, like 1 molar solution of sodium chloride, has twice the osmotic pressure, because it has twice the particles, as something like a mole of sugar, because sugar is covalent, so it's not going to separate. So a mole of sugar solution versus a mole of sodium chloride solution, even though it's 1 mole and 1 mole, they're not the same concentration of particles. So they don't exert the same osmotic pressure. So if you were going to give somebody an IV bag, it would not be appropriate to look at those as having the same overall concentration, even though they're both 1 molarity, right? They're both 1 molarity, so it sounds like they're the same concentration, but if you're looking at particle units inside of that bag, the sodium chloride is twice as concentrated, and that's important. That's, this patient might die, important if you don't know what the right concentration is to give. Does that make sense? Okay. So I know this is maybe not your favorite thing to do today, but yes, you have to remember how to identify this is ionic, this is ionic, this is ionic, but it's two covalently bonded polyatomic ions that are associated. This is just covalent, right? How are you going to remember that sodium chloride is ionic and not covalent? What do you look for? Right, so Sarah says sodium is in group 1, so it's a metal, and every time I've got a metal with a non-metal, then that is going to be ionic, right? Whereas CH4 has 2 different non-metals, so I can expect that to be covalent. And then what about this guy? Those are all nonmetals. How do you know? Yeah, this one you just have to memorize, right? This is why I had you memorize your polyatomic ions. And it wasn't because I was never going to ask you about them again. It's because we're going to see them again and again and again. So you have to be able to look at that and kind of instantly recognize, hey, I see the ammonium polyatomic ion. I see the nitrate polyatomic ion. That is an ionic compound. Okay. All right. So we've got to practice this because we've got more to cover, but let's do at least one problem here. All right, calculate the osmolarity of the following solutions. This is again from your worksheet. If we've got 270 grams of sodium chloride in 3.8 liters of solution, or if we have 1.25 moles of that's sugar in 5.4 liters of solution, to calculate the osmolarity, you're going to remember step 1, calculate molarity, which you guys should already be really good at. And then we're going to multiply by the number of species that dissociate, if any. And then that's it. I guess that's step 2. All right, that's how we're going to do it. So molarity is what units? Moles per liter. So if I have 270 grams of NaCl in 3.8 liters of solution, how do I get to moles per liter? I'm going to need the molar mass, right? So add up the mass of sodium, 22.98, plus chlorine, 35.45. And I get 58.43 grams per liter. Sorry, grams per mole, excuse me. And I'm going to put that upside down. 1 mole NaCl, 58.44 grams NaCl. And so 270 divided by 3.8 divided by 58.44. And I get 1.215. Okay. Hang on a second, I didn't cancel. Molarity, NaCl. Great. Now, Sarah said, look, step 2. I've got 1 sodium ion and 1 chloride ion, so I'm going to multiply that by 2 for step 2, and that gives me 2.43 osmol NaCl. As simple as that. So the molarity part you've already got, or you will get. And then there's just this step. Is it ionic or covalent? If it's ionic, how many individual ions am I going to have running around in solution? All right, what about this guy? First molarity, I need moles per liter. Oh, that was so nice. It's so easy. I was given moles in liters. That's easy. 1.25 moles. That's sugar. It's easier to write. 5.40 liters of solution. Okay, that gives me moles per liter, which is 0.23. Molarity sugar. And Sarah notes that it does not dissociate, so I could multiply that by 1 to give me, oh yes, it's still a 0.23 osmolarity solution of sugar. Right? Was that hard, or was that actually easier? Okay, well, good question. How do I know it doesn't dissociate? Well, the C, H, and O, all of these are nonmetals. And there's not like a polyatomic ion here that I have memorized. So, and obviously, I would not actually give you a polyatomic ion you haven't seen before. That would be massively unfair. So you're going to say that's a covalent compound. It's not ionic. Covalent compounds don't dissociate, so it just states what it is. And it's just the one thing is the one thing that's running around in solution. Instead of what looks like one thing is actually two things running around solution, which is what you get with the ionic compound. Does that make sense? Yeah. Yes, Erica. Every covalent compound is just like a 1 mole equals of that covalent compound equals 1 mole of particles. And if it's ionic, yes, you just assume it dissociates and you count the number of ions. And not just, oh, I've got 1 sodium and 1 chlorine, but like if I've got MgCl2, that's 1 magnesium and 2 chlorines that will dissociate. So that would be 3 particles. Okay. Now, the next piece here that I want to talk about is other colligative properties. So a colligative property is a fancy way, it's a fancy name, colligative property. It's a property of solutions that a solution gets by becoming a solution instead of a pure solvent. Like, how does water change when you put a solute in it? And osmolarity is one of those properties, right? It starts to exert osmotic pressure on its surroundings if they have like different concentration units, right? So that's one thing that happens when you have different concentration units here. All right, so other properties include, and you have to know these, I'll just write this here. Colligative properties, physical properties of solutions which change with the presence of solute particles. So we've already established that osmotic pressure is one of those. For another great example of osmotic pressure, by the way, if you guys want to do this at home, take a little dish of water, and it's even better if it's like really pure water, like distilled water, and put a gummy bear in it. Because unlike other candies, a gummy bear actually has a very thin semi-permeable membrane around the outside of it. So the gummy bear doesn't just dissolve in the water. Instead, because of course it's a very concentrated sugar solution, it will draw the water into itself, and the gummy bear like turns into a giant gummy bear monster. It's kind of exciting. It looks delicious, but it tastes terrible, actually. I would recommend not eating it. But then again, you know, for science, if you want to verify, I can attest to that. All right, so osmotic pressure is a physical property of solution that changes because of the presence of the solvent particles. But additionally, we have freezing point depression, which is a fancy way of saying the freezing point of water is going to go down as you add solute particles. Always down, it never goes up. And boiling point elevation, which is to say the boiling point of water is going to go up when I add solute particles. It never goes down. And vapor pressure depression, which I'm not going to talk about in a lot of detail. But vapor pressure is related to boiling. So basically the harder it is to boil, the less vapor you're going to get. That kind of makes sense. I need to close parentheses or I'm going to go crazy here. Okay, there we go. So these are colligative properties. We already talked a little bit about osmotic pressure, and now I just want to do a couple of practice examples using freezing point depression and or boiling point elevation here. Okay, so, and before I give you specific problems, let's talk a little bit about this. We see this every winter. This is why we put salt on the roads when it's snowy or icy, right? So if the water freezes at 0 degrees Celsius and it's frozen and you put some salt on it, the spots where the salt is sitting on the ice makes a little solution that's very concentrated with salt. The freezing point goes down. And then it's very cold outside. It would normally be frozen, but since the freezing point went down, that little piece of ice will melt and hopefully run off the road. And eventually all of the ice will melt and run off the road or get chipped up a little bit more easily because now it's got little holes in it. And that'll make the road safer to drive on or your walk safer to walk on, like as for instance. Does that make sense? This is why we put salt on ice on the roadways in the winter. Okay, so NaCl is great. You can imagine actually using MgCl2 is going to be 50% more effective because the osmolarity of MgCl2 is going to be 3, right? You have 3 instead of 2 ions with the sodium chloride is more effective, but also more expensive. So you kind of have to weigh, like, is the expense worth the increased effectiveness there? In some places, even putting sodium chloride, the freezing point depression is not sufficient to get it all the way down, which is why Zach says, look, if I'm in Montana, actually it's so cold, sodium chloride's not going to get you past the freezing point, like the temperature that it is outside. So at some point you might just have to use some sort of other mechanical traction tool. So you might use sand there as an alternative. Sand is probably a little bit more eco-friendly too, because then it doesn't melt off and run off the roadways. But yeah, that makes sense. So this is a great example of freezing point depression here. And Sarah is giving us a couple of examples of boiling point elevation. So like, for instance, if you put salt in boiling water to make pasta, it makes it boil at a higher temperature, so it boils a little bit hotter and maybe makes the noodles taste better. It's true that putting a little salt in boiling water will increase the boiling point, which increases the temperature at which the pasta is cooking. You will see this, for instance, sugar in candy making, right? You might have a very high concentration sugar solution in candy making. And of course, as the water in the solution evaporates away, then it becomes more concentrated and that boiling point increases and increases and increases. So that gets to be a very hot solution as well. So these are kind of some specific examples to where you might see. All right, so I've got a question here. We're going to go through this practice problem. Okay. If the boiling point of water increases by 0.51 degrees Celsius for each mole of solute per liter of water, so this is your little formula here, what would the new boiling point of water that contains 8.56 grams of lithium chloride and 75 milliliters of solution, what would that be? Now, there's actually a formula for this, and I thought if I give you this, you can do dimensional analysis and not use a formula. But I found that students actually prefer the formula. So I'm not going to give you the formula on the test, but if you want to memorize it beforehand, that is totally fine for you. And that is the change in temperature. Change in temperature, hang on a second. We've got the boiling point constant, that's K sub B, times the osmolarity. That's going to be the change in temperature. So if you just add that to the initial boiling temperature, which is 100 degrees Celsius, then that will give you the final new boiling temperature. New boiling temperature. And for the new freezing temperature, that's going to be the freezing point constant, and this is kind of unique to everything. I would never have you memorize these. Again, times the osmolarity, and then you're going to subtract that, right? Because this is always a depression. Subtract that from the original freezing point, which is what for water? 0 Celsius, perfect. Whoops. So 0 Celsius minus my freezing point depression constant multiplied by the osmolarity. Okay, so, and this is that constant, 0.51 degrees Celsius per osmol. That is the boiling point constant. That's KB right there. KB. All right. All right, so what's the new boiling point of water that contains 8.56 grams of lithium chloride and 75 milliliters of solution? This was just me being really rude and being like, well, I know you have to find osmolarity, but I'm going to give them grams and milliliters just so they can practice finding molarity, right? Right? So where are we going to start for this problem? And I can see, by the way, I'm going to go just a tiny bit over time today. So if you're like, I have to go, it's okay. This is going to be recorded and posted. And I apologize for being just a little bit over time. 8.56 grams LICL. My target here is going to be moles per liter, right? So to get from grams to moles, and this is liters. So 1,000 milliliters in 1 liter. Okay. And if I look at my periodic table over here, lithium is 6.941, chlorine is 35.45. So I get 42.391. Good. Nicole got that too. Always feel better when somebody else gets the same answer as me. So 1 mole of LICL, 42.391 grams LICL. And my grams cancel, and milliliters cancel, and hallelujah, I have moles per liter, so that's molarity. And what do I do next? I want to know the new boiling point. I'm going to use this equation. If I look here, it gives me osmol. How do I get from molarity to osmol for this thing, LICL? Multiply by the number of particles. Yes. How many are there going to be for lithium chloride? 2. 1 lithium ion, 1 chloride ion. Okay, so multiply that by 2, and that gets me 5.38, yeah. Oh boy. Osmol LICL. Good. And now we can plug it in here and say, okay, if we have 0.51 degrees Celsius per osmol, which is basically what that says, that's my KB. Multiply that by my 5.38 osmol solution. That tells me my boiling point is going to increase by 2.75 degrees Celsius. And if my original was 100, then I'm increasing that by the 2.7, and I get a final boiling point of 102.75 degrees Celsius. Great question. Sarah says, do we need to convert to Kelvin? The answer is no. Nope, because we're not multiplying our temperatures or dividing our temperatures. This is just a relative change in the temperature size. And so we could just leave it in Celsius. Okay, I'm sorry that put me a little bit over time, but that should take you on your worksheet. That's going to take you, let me just show you what is left here. Section 5 on your worksheet is doing exactly this. Now section 6 on your worksheet we're not going to get to, but what I want you to see, this is taking what we just learned about solution concentration units and plugging them into our stoichiometry equations that we already did in chapter 6. So there's nothing new here. We're just putting it together. So if you consider the roadmap that we typically use, right? So our little roadmap, open you up here, right here. To solve these problems, essentially what you're going to do is say, hey, look, I have moles on this roadmap. And what I learned to do in this section on solutions is that if I have moles, I can take the volume in liters and find molarity, which is moles per liter, right? And I can do the same thing here. So we're going to go off-roading. But again, this is specific to solutions. So I could give you, say, molarity, concentration, and a volume of one thing and ask you about grams of another thing, right? Instead of going from grams to grams, we could go from solution to grams. Just like as we saw in our last chapter, if you were a gas, you could go off-roading this other direction. And from moles of a gas, we could use pressure, volume, and temperature to, or PV equals nRT, to get pressure, volume, or temperature. You guys remember that? Do the same thing here, but of course it would be A. Okay, so that is what we are doing on this very last section on the worksheet right here. If I'm starting with grams of this space and I'm going towards volume of the acid, or in this case, I give you the concentration and I'm looking for volume and I'm telling you the concentration and volume of another solution that was there. So in that case, I'm doing, I'm going to go like this direction, okay? Anytime I can go through moles, I can add it to my roadmap. Isn't that exciting? And the very last problem, I think, on that worksheet, just to show you, is an aqueous solutions that are reacting together to form a gas. So here I give you volume, I want to know concentration, and I give you the pressure and volume and temperature of the gas that is formed. Oh, isn't that exciting? You get to go from pressure, volume, and temperature of the gas that's formed back to the concentration of the reactant that was used to make it. Okay, I'm gonna let you guys go. I'm sorry to keep you over time. And I want you to practice these last ones. I know we didn't get to them, but it's everything that we've already done. We're just putting it together. I want to see where you get with those. And I hope you guys have a great day.